oxide of carbon monoxide hydrogenation over oxidized molybdenum sulfide catalysts. The authors are Jae Sung Lee, Hee-Choo Yoon, In-Sin Nam, Yong-Shik Chun, and Young-Do Kim. And the author is Jae Sung Lee.
Mr. Chairman, it's my pleasure and honor to have a chance to present my paper in this fine meeting. And the paper I'm going to present this morning is a result of collaboration among our colleagues at POSTEC, Professors In-Sin Nam, Dong-Sik Chung, and Young-Do Kim. And majority of the experiment was carried out by Dr. Hee-Chul Woo, who was a former graduate student and now the professor at the Busan National University of Technology. The alkali promoters are widely used in catalytic CO hydrogenation reactions, and their effect could be summarized shown here, and various explanations are proposed to account for those observed effects. Looking at the literature, we learn that depending on the situation, one promoter exercises an effect or another. So the questions we had, and the one I tried to answer this morning is following. How does the same alkali element, doped on a catalyst, sometimes serve the chain growth for the product, but promote alcohol formation in other cases? In other words, what is the important variable determining the effect of the promoters? The catalyst system we are dealing with is unsupported molybdenum sulfide, which was prepared by thermal decomposition of ammonium thiomolybdate, and alkali compound was added by impregnation with the potassium to molybdenum molar ratio of 0.5. Some of this catalyst was oxidized by exposing the catalyst into the atmosphere for a extended period of time. So the fresh catalyst in this presentation is the non-oxidized catalyst right after preparation, whether or not it is used for the reaction. Okay. This catalyst was tested for CO hydrogenation reaction and examined by a number of the spectroscopy techniques. This catalyst are well known for making a mixed alcohol out of syngas, as patented by Dow Chemicals and Union Carbide, and it's extensively studied by the Professor Clear's group sitting here. And in our cases, we studied the reaction in the conventional high-pressure flow reaction system, and product was measured by GC. So we employed a number of potassium compounds and studied their steady-state activity and selectivity of CO hydrogenation. The unpromoted molybdenum sulfide produced mostly hydrocarbons with very little alcohol. Now the C2 plus, namely the fraction of the product heavier than the C2 versus methane was 0.72. If you add potassium carbonate, hydroxide, acetate, and nitrate on this catalyst, you now see substantial decrease in activity and formation of alcohol with a good selectivity. On the other hand, if you employ potassium sulfate and halogen compound, you now do not produce much of the alcohol and produce most of the hydrocarbons. But the product distribution is not the same as the unpromoted molybdenum sulfide, because we are producing now high molecular weight hydrocarbons as reflected here. Now, if you the oxides, this is the carbonate and hydroxide in the atmosphere. Now you see the substantial increase in CO conversion in catalyst turned from the alcohol selective catalyst to the hydrocarbon selective catalyst with the extended chain length. So here you have a system depending on the potassium complex employed, and depending on the pretreatment condition, you have either the chain loss promoter or alcohol promoter. So what is the variables that separate this effect? One correlation we found was that the activity for alcohol formation versus the pKa values of conjugate acid of this compound. Namely, the alcohol formation, the promoters, had high values of positive pKa values. On the other hand, chain promoter had the negative values of the pKa. So this is certainly a variable you have to consider. Now we examined this catalyst with the scanning electron microscope with the capability of the quantitative analysis. This is the same image, and these three photos is so-called X-ray map. So whiteness of this indicate the relative concentration of each element. So in the case of the potassium carbonate, though molybdenum sulfide, after CO hydrogenation reaction, you will see the molybdenum and the sulfur distribution, which reflect the exact morphology of the particle itself, which is the natural, because the particle you are looking at is essentially molybdenum sulfide. But the distribution of the potassium itself also reflects very well the morphology of the molybdenum sulfide particle, indicating that the potassium has a very uniform distribution of the molybdenum sulfide particles. The same phenomenon was observed when the potassium, the hydroxide was employed. So this uniform distribution seems to be a characteristic of the alcohol formation promoter. On the other hand, the chain loss promoters, such as the potassium sulfate and KCl, shows a highly non-uniform potassium distribution. Sometimes they even make big particles of their own, as the white particles indicate. So this the difference in distribution seems to be a factor determining their selectivity, and could be correlated to the previous pKa values. Namely, with the alcohol selective promoters, they lose their counter anion easily under reaction condition and distribute themselves uniformly over the molybdenum sulfide surface. On the other hand, the chain loss promoters, as will be shown shortly, will maintain their initial chemical state during the reaction. This difference in distribution may be reflected in this mode of reaching steady state in these promoters. All the alcohol promoters show the substantial decrease in CO conversion in the initial 3 or 4 hours. And during this period, initially hydrocarbon selective catalyst turned into the alcohol selective catalyst. On the other hand, the chain loss promoters didn't show any significant change in activity and selectivity. So it seems that this time required to reach a steady state is the time required for that the potassium species spread itself over the molybdenum sulfide surface. The oxidized catalyst shows that the steady increase as the time of exposure increased. And during this period, you observe the initially alcohol selective catalyst turned to the hydrocarbon selective catalyst, and the chain length increased steadily. We observed this catalyst by XPS to see the surface state. We found that the part of the molybdenum 4 species from MoS2 turned into the molybdenum 6 species, as this shoulder indicates. At the same time, the sulfur species, initially the sulfide, changed to the sulfur 6 species, probably sulfate species, as the exposure of the catalyst to the atmosphere is extending. Now, if you see the surface of this catalyst with infrared, you can see how the surface species changes. Starting from the potassium carbonate, you observe the carbonate peak, and then after 5 weeks, you observe the sulfate peak with TD symmetry, like the potassium sulfate is shown here. Upon further exposure, after 13 weeks, the part of the TD symmetry species changes to C2B species. So definitely you have the sulfate species on the oxidized catalyst. So what you are seeing is that the oxidation of molybdenum sulfide by oxygen and water present in the atmosphere. One consequence of this oxidation is the redistribution of the potassium species. Okay, here we show the quantitative analysis of the molybdenum sulfur potassium component by OJ electron spectroscopy and X-ray energy dispersal spectroscopy and chemical analysis. And we are all aware that into this order, the technique probe the increased depth of the sample. And for the fresh catalyst, you see the potassium distribution like this, not much different each other. On the other hand, oxidized catalyst show the depletion of the potassium on the surface. Seems that the segregation of the potassium has occurred on this catalyst. This oxidation and segregation of the potassium have been reported in semiconductor literature. Namely, if you start from the alkali promoted MoS2, upon exposure to oxygen and water at room temperature, the oxygen diffused into the bulk to oxidized molybdenum sulfide. And then potassium pick up the oxygen from gas phase and then supply them into the bulk. This role of potassium has been termed the oxygen sponge. And during this process, some part of the potassium diffused also into the bulk, and resulting in the exposure of the uncovered molybdenum sulfide surface. Now, if you look at the lateral distribution of potassium for this oxide catalyst, you see now much better, much uniform distribution of potassium relative to the chain growth promoter, but not as good as the alcohol promoter, because now you cannot see the morphology of the original particle. And you also have to remember that some of this signal must come from the potassium which is present in the subsurface regions. As I mentioned, the chain growth promoters, such as the oxidized potassium carbonate or the potassium sulfate, maintain their original chemical state even after the reaction. On the other hand, alcohol promoters, such as potassium carbonate, shows a new peak after the reaction. You can see this difference much more clearly in the case of K2S, which is another alcohol promoter. Before the reaction, you see the peaks which is coming from the K2S, But after the reaction, these features disappear, and you have new strong peak in this region, which could be assigned to be a bicarbonate species. In fact, all the alcohol promoters shows these characteristic two peaks irrespective of their initial state. So it seems to be that the alcohol promoters not only distribute uniformly on the surface, seems to form common intermediate, which must be an active species for the reaction. On the other hand, chain growth promoters maintain their initial the chemical state and seems to aggregate with itself or show a very pure distribution. Now, how we can rationalize this observed phenomena with difference in selectivity. So let us consider this very simple scheme, which is accepted by many people for the formation of the product in the CO hydrogenation reactions. So from this hydrocarbon intermediate, in order to form the alcohol, you have to do the two things. First, you have to kill or block the hydrogenation site, which is in competition with the alcohol formation. The alcohol promoter seems to achieve this by uniformly distribute over the molybdenum sulfide and blocking the hydrogenation site. Also, you have to activate carbon monoxide molecularly and also promote insertion of this species into this intermediate to form the alcohol. On the other hand, in order to form hydrocarbons, you have the large areas of the unpromoted surface. You can achieve this by maintaining poor distribution of the potassium compound, or the promoters can diffuse into the subsurface layer, exposing the unaffected molybdenum sulfide surface. But this exposed molybdenum sulfide is not the same as the unpromoted molybdenum sulfide, because they produce more the heavier hydrocarbons. This seems to be the role of classical electronic promoter of the potassium, which is quite widely observed in case of the group A metals. And it is understood that alkali promoters provide electrons to the metal, and electron-rich metals accelerate CO dissociation. And if you increase the rate of CO dissociation, you increase the population of this kind of hydrocarbon species, and you also increase the chance for the chain growth. In this regard, you have to remember that the conventional Fischer-Tropsch catalyst require very small amount of promoters, usually less than 1%. On the other hand, in order to be an effective alcohol synthesis catalyst, you require large amount of promoters, usually more than required for complete coverage of the surface. So, to conclude, the distribution of the promoter is one of the primary factors, at least, determining its role in catalytic CO hydrogenation reactions. To be more specific, in order to be an alcohol selective catalyst, you require fertile removal of counter anion to form sites for molecular absorption of CO, or probably promoting CO insertion. Secondly, uniform spreading of the species to block the hydrogenation site. For the chain growth promoter, you want a minimal coverage by the promoter and electronic modification of the main catalytic component is required. Thank you for your attention.
Now the second talk is open to discussion.
alkyl. Those alkyl, you convert their anions into a reactive anion that participates in the synthesis. There are some that don't do that, like chloride or sulfur. But then how does the correlating pKa work? All those compounds of anions, such as initially sulfide, hydroxide, or carbonate, convert to the same species.
Okay, the chloride and sulfate quite stable compound. Right. So
I'm referring to the difference between, let's say, hydroxide and carbonate on the correlation.
I think the difference between hydroxide and carbonate is very small. The 14%. So I think that's roughly you can divide to the alcohol hormone versus the hydrocarbon hormone. I don't pay attention to the small difference in the effect.
And you do not have on that correlation graph potassium sulfide.
Sulfide, we didn't have the yeah, right.
Your work is very nice. I think the sulfate is very important results. Have you tried the catalyst which deposes some molybdenum sulfate? So your sulfate should reduce by oxidation of molybdenum sulfide. Second question is, you mentioned that the catalyst is very active, maybe this is for alcohol formation. Sometimes we believe the catalyst is innate or expected. So do you have any other evidence for your conclusion?
I think I understand the second question clearly, so let me answer that one first. Yes, if you look at the literature, same compounds sometimes promote the alcohol and sometimes promote the training dose. I think that if we extend our conclusion, our work, that might be reflect how the promoter is distributed over their specific catalyst. And I don't catch your first question.
First question is, I just give you a suggestion. Have you tried the catalyst which deposits some molybdenum sulfate on the surface, and how was the result?
We didn't do that on purpose, but the infrared says that we have the sulfate species, all different kind of sulfate species. So for the oxide catalyst, you have two effects: a small amount of potassium on the surface in the form of sulfate, and also the potassium which is the present in the subsurface region. So I think we have the two effects of the
The last question.
Have you anything about the activity of your practice? Or do you think it will play have a role have an effect on product production? And my second question is my first question is do you have anything about the activity or specificity of your assets? And do you think it will play a role on the product distribution? And my second question is in your explaining, you said the alcohol and the hydrocarbon products in different ways are parallel. Do you think the alcohol will be converted to hydrocarbon in the reactor or on the
first question, what is the effect of acidity in my catalyst? Because the sulfate in the C2B the state can promote the superacidity of the catalyst, but we didn't see any correlation for the acidity. Second question is the probability of changing from alcohol to hydrocarbon to conversion. So we compare the product selectivity at the same conversion. I usually show you. But yes, there is